All right, let's take a look at some practice problems from chapter 1. This is question 1.39. It can be found in the practice problems section, which is towards the end of the chapter. So if you look after it's section 1.13, then you have a review of concepts and vocab. Then there's skill builder review, and then you have practice problems. So the first one that I want to take a look at is just draw some Lewis structures. And when we're given a formula like this, you can see that not all of the carbons and hydrogens are bunched together, right? This is what we call a condensed molecular formula, which actually gives us some information about the way that the atoms are connected together. Let me explain what I mean. If we were to just tally up the molecular formula for this compound, it would be C2H6O, right? That's just the molecular formula. It just tells us the number of atoms in the molecule. However, you see that they're laid out in such a way that we can actually see that first we have a CH3, then a CH2, and then we have an oxygen and a hydrogen after that. Well, remember that carbon always forms 4 bonds, okay? And we know that hydrogen always forms 1 bond, and oxygen will always form 2 bonds and always have 2 lone pairs on it, okay? So with that in mind, we should be able to put this together. So we see that we have a carbon that has 3 hydrogens attached to it. So I'm going to put them towards the end like this because I have a bond to another carbon like this. That carbon also has 2 hydrogens bound to it like this. Then I have an oxygen, and then lastly, I have a hydrogen. I want to make sure to include my lone pair in there like that. Now, if I was to just give you this molecular formula, well, of course, there's another way to connect those, and we looked at this during our last class. I showed you how to put together dimethyl ether. So when you're given a condensed molecular formula like this, you want to be able to look at that and say, well, I know it's connected in this order. First, I have a CH3, then I have a CH2, then I have an oxygen, and then a hydrogen. So over Microsoft Teams, it's a little challenging for me to ask you guys questions, you know. But I have a question about this next one here. So this is 1.39b. You can see that we have a CH3, and then we have a carbon and a nitrogen. I'm going to give you a second to try drawing the Lewis structure for this molecule, and I'm going to tell you that inside this molecule, there is a multiple bond. There's either a double bond or a triple bond in this molecule. Could anybody tell me, which type of bond I would find in this molecule, a double or a triple bond? Yeah, there's a triple bond in the molecule. Absolutely. Right? Absolutely, right? Because we know that carbon always has 4 bonds. But you see that the way that it's laid out, you have a carbon attached to 3 hydrogens, right? Then you have it attached to another carbon and then a nitrogen. Well, we know that nitrogen always forms 3 bonds, right? 3 bonds, and it always has a lone pair, and carbon always has 4 bonds. So the way that carbon is written right now, it's only got 2 bonds. That is not enough. And so we can't put another bond here because this carbon already has 4 bonds. Therefore, we're going to put 1, 2 bonds like this, and then we're going to put the lone pair like that. Okay. Now notice that I didn't take the, kind of Gen Chem 1 approach to doing a Lewis structure where we first tally up the total number of valence electrons, which we could have done. Okay. I could have just added up the number of valence electrons. However, since we're given a condensed molecular formula where they show us the connectivity of the molecule to some degree, we don't have to do that. Now, if you want to do that, that's totally fine. You can absolutely do that. But I would say it is not necessary with these particular examples. All right, I got another question for you that I think would make a good quiz question. And this is question 1.42 from our textbook. They show this really interesting molecule. It says, draw the only constitutional isomer of cyclopropane. So let me show you what cyclopropane is. Okay, so you've all heard of propane before. Right? It's a gas that's used oftentimes as a fuel for heating and using barbecuing. So this molecule here is called cyclopropane. It has a molecular formula of C3H6. There is another way. There's only one other way that I could put these atoms together to make another molecule that has this molecular formula, C3H6. Could anybody tell me how I might do that? Excuse me. Could anybody tell me what kind of strategy I might take? Yeah, good answer, Kyla. Okay, that's a good one. Yeah, absolutely. So Warren and Kyla are on the right track, right? They're saying, well, what if you put the 3 carbons together like this, and then just started putting hydrogen? So we have 1, 2, 3, 4, 5, 6. I'm just going to kind of spread them out like this. Now you probably noticed that I kind of did an end run here, right? I didn't end up putting one here because that would get us in trouble. That wouldn't really help us put our molecule together. But my students are saying, put a double bond, and you're absolutely right. If I put my 6 hydrogens like this and I put a double bond like this, there you go. Now I have a constitutional isomer of cyclopropane. This is called propene. And we'll talk about the nomenclature of these types of molecules later on. But that's the only other way that I can connect these together. Now, a trap that I'm sure that most of you are, starting to understand, that you wouldn't fall into this by now. But I just want to point out, in case anybody's struggling, if you say, well, Mr. Dion, what if I connect the atoms like this? Okay, I put the double bond on this left-hand side. Could anybody tell me why this is not considered another constitutional isomer and it's not a trick question?
Because like if you turn the molecule in like a 3D, it would be the same molecule.
Yeah, absolutely, right? If you were to literally, make a model of this and take your human hand, right, and stick it under there and flip it over 180 degrees like a pancake, you'd end up with that, right? It's identical. So it's another way of saying that these two are identical. Okay, these are the exact same molecule. So you don't want to fall into the trap of drawing the same molecule over and over and saying, oh, it's a different molecule. Yeah. Okay, great. You guys are giving me great answers. This makes me really happy. It makes me feel like my students are understanding, which is a good thing. Let's try something maybe a little trickier. I'm just looking at the problems here. Let's take a look at 1.43. I think there's some good problems in this one. It's just asking us about, determine whether the molecule below exhibits a molecular dipole moment. So this is 1.43. So the question is just, does the molecule have a dipole or a dipole moment? And it means an overall dipole moment, not are there polar bonds, right? Let me try a couple with you. So let's say we do CH4. Okay, well, the carbon is surrounded by 4 hydrogen atoms, right? It's got no lone pairs, and so it's going to be a tetrahedron like this. Okay, could anybody tell me, will this be a polar molecule or a non-polar molecule? Or does anybody have a guess even? Yeah, thanks, Benjamin. Absolutely. This is a non-polar molecule. Now, the reason why is because carbon-hydrogen bonds are non-polar. All right, so nothing more than that, really. But even if they were polar bonds, they would all cancel out. Let me show you an example. If you had, let's say, carbon tetrafluoride, right? Then you'd have really polar bonds in your molecule, wouldn't you? Very polar bonds. Okay, but if you had this molecule that is a tetrahedron, or has a tetrahedral molecular geometry, we have a dipole going this way, one going this way, one coming out here, and one going off into the back like this. And then the dipoles would cancel. Dipoles cancel. So therefore, this would also be nonpolar. Let's try another one. What's the next one? Ammonia, water. Let's try carbon dioxide, CO2. So if I try D, carbon dioxide, and I know that some of these might be simple for you, but I want to make sure that we take a look at them before we just start blasting into chapter 2. Carbon dioxide, if you draw the Lewis structure of carbon dioxide, we have 4 electrons here plus 6 electrons times 2. So that gives me 12 plus 4, which gives me a total of 12. It gives me a total of 16 valence electrons. And we put all that together, you end up with this molecule, right? There's 2 regions of electron density around the carbon, or you could say the steric number is 2. And so this is a linear molecule, right? It has a bond angle of 180 degrees. The molecular geometry is linear. Are there polar bonds in carbon dioxide? Yes or no? Yeah, absolutely. There's definitely polar bonds, right? The reason why there are polar bonds is because oxygen, let me use a different color here. Oxygen has an electronegativity of 3.5. Carbon has an electronegativity of 2.5. So the difference in electronegativity is going to be 3.5 minus 2.5, which equals 1.0, which is a polar bond, right? But since the molecule is linear, get my object eraser. There we go. So since the molecule is linear, you have a big dipole going this way, but you have another one that's going in an equal and opposite direction. Right? If you tally up those two dipoles, if you add them together, what's going to happen? They're going to start to C ends with ancel. They're going to cancel each other out. So we'll just put here dipoles cancel. Nothing more than that. Let me give you another example of a linear molecule. CS2, which is called carbon disulfide. You got carbon dioxide, carbon disulfide. Well, sulfur, it comes just below oxygen in the periodic table. It has an electronegativity of around 2.5, right? So, I mean, these bonds aren't polar anyway, but the same rationale would apply here. You can imagine that even if these bonds were slightly polar, and they probably are a little bit polar, I mean, a tiny bit, they would cancel out. Okay, so linear molecule like that, that's symmetrical, the dipoles would cancel. All right, let's take a look at one more. Let's try F. So CH2Br2. So F, so this is 1.43, and it's F, which is CH2Br2. I'm going to give you a second to think about this one. And if anybody can tell me if this is a polar or non-polar molecule without looking at the solutions manual, just type it in the chat, or you can unmute your mic. Would this be a polar molecule, yes or no? Okay, I'm getting some different answers here, so let's take a look at it. Remember that hydrogen always has one bond, right? We know that halogens in organic chemistry are always going to have one bond. So if we draw out the molecular geometry, I'm going to draw the two bromines in the plane of the screen. And then I'll put one hydrogen going back like this and the other one coming out. So it's tetrahedral, right? Are there dipoles in the molecule? Absolutely there are, right? We have a dipole going this way towards this bromine, and we have another dipole going over here. So if we tally those up, the overall dipole is in this direction. So this is a polar molecule. Yes. Okay. It is a polar molecule, right? Those dipoles are not going to cancel each other. They're going to add together to give you a resultant dipole that's going off in that direction. All right. Let's take a look at another one here. Let's try 1.49, and we're going to do it a little bit quickly, but I just want to cover a little bit about bond angles with you guys. So we already looked at this molecule earlier on today, so I'm just going to draw the Lewis structure kind of quickly here. So just bear with me for a second. This is a Lewis structure. It is not drawn showing, you know, all the bond angles, but could anybody tell me what the bond angles are on this carbon? Could anybody tell me what the bond angles are on this carbon that I have the red arrow pointing towards? Yeah, exactly. All the bond angles are 109.5 degrees, right? Because the steric number of that carbon is 4. Therefore, its molecular geometry is tetrahedral. What about this carbon here? If I highlight this carbon with a blue arrow, what would be the bond angle on that carbon? All the bond angles on that carbon are all the same, I can tell you that. And what would they be? Yeah, thanks, Kyla. Exactly. They'd be 109.5 degrees. Why? Because the steric number is 4. What about the oxygen? Can anybody tell me what there's one more bond angle, right? And it's the one on the oxygen, right? There is a molecular geometry associated with the oxygen. Can anybody tell me what the bond angle would be right here? The way it's drawn, it looks like it's linear, but it's not. This is just a Lewis structure. It's not drawn in 3 dimensions. What would the bond angle be here? Slightly less than 109.5 because of the lone pairs. Absolutely. So we'll put here less than 109.5 degrees, and that is absolutely correct. All right, if we just zoom in on that part of the molecule, right, we have the carbon, then we have the oxygen, and then we have the hydrogen, right? And you're going to have, let me draw it like this. We have the oxygen, which is going to have a hydrogen, it's going to have a carbon, and you're going to have one lone pair in the back, and you're going to have another lone pair like this, right? So that bond angle is slightly less than 109.5 degrees. Exactly. Exactly. Let's try another one. Let's try H. We drew this molecule earlier today. This is called acetonitrile. It's a really polar molecule. I worked with a guy, it was his favorite molecule. He used it as a solvent for everything. So this one, we know the bond angle is going to be 109.5 because the carbon is sp3 hybridized. Its steric number is 4. It's tetrahedral. What about this carbon here, the one with the triple bond attached to it? Shoot. Could anybody tell me what the bond angle around that carbon would be? The one that I have with the blue arrow pointing towards, the one with the triple bond. Yeah, it's going to be 180 degrees. Absolutely. Yes, it's going to be because its molecular geometry is linear, right? Because it's got a steric number of 2. Right, it's got 2 sigma bonds and no lone pair, so therefore it is linear. We'll try one more, C2H4. So this is C. So let's see here. C is C2H4, and we've drawn this molecule a couple of times. When you have a double bond on a carbon, so both of these carbons are identical, but who could tell me what the bond angle on this carbon would be? It's got a steric number of 3, no lone pairs. It's sp2 hybridized. Thanks, Warren. It's 120 degrees, right? It is trigonal planar.